All right, so today we'll be talking about universal gravitation. I've missed all of you, and hopefully I'll see you soon. So we all have heard the story that Newton discovered gravity, but did Newton really discover gravity? I'm going to give you a hint. He did not. Right? The cavemen knew that throwing someone off a cliff was a bad idea. So they knew that if you drop something, it falls towards the ground. So the cavemen knew about gravity. People before Newton knew about gravity. What Newton did was more important, it was more special. What he discovered is that gravity is universal. Now, what does that word mean, universal? Well, if we go back to our opening slide here, universal literally means that it exists everywhere in the universe. So Newton proposed that all objects in the universe are attracted to all other objects. Now, I think you've all heard the story about Newton and the apple. Sitting in an apple orchard, apple falls on his head, and that's when he quote unquote discovers gravity. Okay, well, that didn't really happen like that. And by the way, the original story came from a biographer of his. His name was William Stukeley, and this is a page from the original copy of that biography, where he's talking about sitting with Newton. They were having a discussion, and Newton recounted how he was sitting in an apple orchard, and he saw an apple fall. Didn't hit him on the head, but he saw an apple fall, and he wondered, why do apples always fall in straight line paths towards the center of the earth? So they always fall in straight line paths towards the center of the earth. They don't go perpendicular. They don't go at an angle. They always fall straight down. And he recounted to his friend that that's what led him down the path of figuring out if gravity was a universal force between all two objects. Now, one of the big objects that was involved in his thought quest was the moon. So the moon and the earth are tied to each other. That force that holds them together is gravity. And so Newton wondered whether that same force that pulled the apple towards the center of the earth also pulled the moon towards the center of the earth. And the moon is actually falling around the earth. That's something that we'll talk about soon. So this story about the apple that you've heard, my fifth grade version was, that the apple fell on his head, he discovered gravity. That was not what happened. But if Newton was out there, and we can only believe what he said, then it was that observation, that aha moment that he had, that the apple was attracted to the earth. Now, so Newton theorized that all objects in the universe are attracted to each other. So I have a group of physics students sitting here in a lab. Now, why aren't they feeling the attraction between each other? So why aren't you feeling the attraction between the person you're sitting next to in class now? If Newton was right, there is a physical force of attraction between you. Now, we do feel the force of attraction between us and the earth. That force we call our weight. So I wonder why we can't feel this force. Now, every year I ask this in class, we talk about it, and someone always comes up with the answer, well, the earth is really big and people are really little. So maybe we can't feel the force of attraction between the people next to us because those masses are just small. Now, that's actually something that Newton worked to figure out. So first off, what Newton found is that the mass of the first object and the mass of the second object, they are directly proportional to the force. That any two masses in the universe are attracted to each other. And then it goes by saying, because we already studied Newton's laws of motion, that the force that's pulling mass 1 towards mass 2 is equal in an opposite direction of the force that's pulling mass 2 towards mass 1. So the bigger the masses involved, the bigger these forces end up being. But the force is always the same between each mass. So mass 1 gets pulled towards mass 2 just as hard as mass 2 gets pulled towards mass 1. Now, if you think about it this way, if your weight is 150 pounds, that means the Earth is pulling down on you with 150 pounds of force. You're also pulling up on the Earth with 150 pounds of force. Now, Newton also found that the distance between the objects affects the force. Now, if you stop and think about it, if the distance between the objects is increased, would you think the force goes up, or do you think it goes down? And if you think about it, you should realize that it should go down. So if the distance is increased between these two objects, the force will get smaller. If the distance is decreased between the two objects, the force gets bigger. Now think about a magnet. If you have the magnets aligned so they're attracted towards each other, if you hold two sets of magnets really far apart, you won't really be able to feel the force of attraction between them. It exists, but it'll be really small. Now, if you hold those magnets really close together, that force gets really big. So if you've ever played the magnet game with your refrigerator magnets, take two refrigerator magnets off your fridge, and you try to hold them as close together before they touch, you know that if they get really close, it's really hard to hold them apart from each other because that force gets pretty big. So the force is directly proportional to the masses. Masses get bigger, the force gets bigger. And then it's inversely proportional to the distance between the masses. Now, we call the distance r. We're going to talk more about this, but the reason we call it r is because a lot of what we talk about when we talk about gravity are objects orbiting each other, like the moon orbiting the Earth. And the distance between the centers of the moon and the Earth is the radius of the circle that the moon makes as it goes around. It's not exactly a circle, but it's really close. Okay, so just to recap, this is what Newton figured out. He figured out that the forces between the objects, they're the same as each other, no matter whether you're on the bigger mass or the smaller mass. Those are always the same. Then he figured out that those forces are proportional to the two masses, and they're inversely proportional to the distance between the centers. Now, they're not just inversely proportional to the distance itself, but to the square of the distance. Now, this has to do with gravitational fields. We could talk about that a little bit, but if I drew field lines out, you kind of think of gravity as extending out in fields like this, but in 3 dimensions. And as we go further and further and further away, this is kind of like a flashlight. At the beginning of the flashlight, if you hold up a sheet of paper, it's really bright. But then as you get further and further and further away, that same amount of light spreads and spreads and spreads. So you hold up that same sheet of paper, not as much light is falling on it. And because that's in 3 dimensions, the amount of light would go down with the square of the distance. Gravity works very much the same way. So if I get twice as far away, if I increase this distance by 2, the force goes down by 4, because that would be 2 squared. If I tripled the distance, the force would go down by 9. It would be 1/9. Now if I made the distance smaller, so if I, instead of r here, I made it r over 2, I made it half r. Another way to think about that is if the distance here was 1, instead of it being 1 meter, I made it half a meter. So if I half the distance, then the force goes up by 1/2 squared. Well, it's 1 over 1/2 squared, so it'd be 4 times. If you made the distance 1/3, the force would go up 9 times. So smaller distance, bigger force. Bigger distance, smaller force. Bigger masses, bigger force. Smaller masses, smaller force. Now, this wasn't easy for Newton to prove. He actually invented calculus so that he could make this proof. And this is where Newton left this equation. So notice this is not an equal sign. You should not write this down on your equation sheet. This is proportional to. So this means that the force is proportional to the two masses divided by the square of the distance between them. It took someone else to actually turn this into an equation with an equal sign. And that somebody else was named Henry Cavendish. With the help of some other scientists, he conducted an experiment to actually find the exact amount of force between two masses. And if you look at the bottom here, this is a replica of what the lab setup looked like. But what he did, in essence, is he took two heavy masses, and then he took two light masses. And these light masses are perfectly balanced on a torsion wire. And there's a little mirror on that torsion wire. Now with the torsion wire, we know exactly how much force is required to twist the wire. So he would get these masses, he would get them ready, and then he would release them, and he would see exactly how much twisting there was. Because this big mass is going to be attracted, oops, that's not what I meant to do. This big mass is going to be attracted to that smaller mass. That smaller mass is going to be attracted to that bigger mass. Same thing will happen over here. And when this wire twists, because they're moving towards each other, it'll twist a little bit. We can measure the distance between the centers. The twist in the wire would give us the force. So I would know the force. I know the mass of the first object. I know the mass of the second object. And then I would know the distance between the two objects. Now if I know that mass and this distance and that force, I can calculate these. And instead of having this be a proportional sign, I can now calculate what makes it an equal sign. And we just need something. In science, a lot of physics teachers or a lot of science teachers will call this a fudge factor. But it's something that's called the universal gravitation constant. And that universal gravitation constant is just a number that if you multiply the masses times it, divided by the square of the distance, it will give you the exact amount of force that's acting on an object. Now the universal gravitation constant is 6.67 times 10 to the negative 11th. So it's an incredibly small number. Because remember, this is scientific notation. This is not, a mathematical operation. It's not intended to be that way. So this means take the decimal and move it to the left 11 places. So if you were going to write this out longhand, it would be 0.000000000. Zero, 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 6, 6, 7. Excuse me. So that's what it would look like longhand. That's not very fun. So instead, we're going to write it out as 6.67 times 10 to the negative 11th. You don't have to add these extra digits. We'll just use 3 significant figures. And then the units here would be newtons times meter squared divided by kilograms squared. Now if you look up here, you should be able to see why. Because force, remember, is always, always, always measured in newtons. Mass is always measured in kilograms. So that's kilograms times kilograms. Distance is always measured in meters, so distance squared would be meter squared. And if I want that to be newtons, then this constant would have to cancel out the meters, so meters has to be on top. It's got to cancel out the kilogram squared, so that has to be on bottom. So these are the units for big G. So big G is the universal gravitation constant. So this is an equation for the universal law of gravitation. This is the universal gravitation constant. That goes with it. Now, one of the reasons why they wanted to complete this equation is because that allows you actually to find the mass of the Earth. Because if I'm standing on the Earth, I know what the force of attraction between me and the Earth is. That would be my weight. I could stand on a scale. I know what my mass is, and I know the distance between the center of the Earth and the surface of the Earth. We've actually known that for a few thousand years. And let me explain how we've known that. So a Greek librarian, he was a librarian at the library at Alexandria, and I'll butcher his name, but it's Eratosthenes. In about 300 BCE, what he figured out was he had heard that there was a well on a certain day, that when the light came from the sun, it went straight down the center of the well. It didn't make any shadow. So if I held a stick at that spot, then it wouldn't cast a shadow. The shadow would be directly underneath the stick. Okay? Now, light from the sun, because the sun is so far away, basically comes in parallel. So all these rays of light that hit the Earth are parallel to each other. Now, because the Earth's surface is curved, in one spot, let's say the equator, I put my flagpole up or my stick, there's no shadow. But in another part of the Earth, I put my flagpole up, there will be a shadow. And that shadow, shadows aren't supposed to be purple. They'll make it purple, right? That would be like the triangle basically formed by the shadow there. Now what Eratosthenes figured out was that in Alexandria, on this day when there was no shadow in a nearby town, the shadow by him was 7 degrees. Well, if we know that this is 7 degrees, we've all taken geometry. I know some of you have taken it during the pandemic, but I know that you remember that angle would be equal to this angle because that line is parallel to this line. So I have an intersecting line. Those are the alternating angles. So if that was 7 degrees, this would be 7 degrees. Now, obviously, that's not to scale, but we'll just pretend. And if I know that there are 360 degrees in the circle, so if I knew this distance right there, I would take 360, I would divide it by 7. And then I would take that distance and I would basically distribute that over the entire circle. So that would give me the circumference. And he was incredibly close to getting the circumference of the world right. So when anybody tells you that Columbus discovered the Earth was round, they're incredibly wrong, because it was done well over 1,000 years before he was alive, almost 2,000 years before he was alive. And they knew the circumference of the Earth to a much greater degree than he did. So we knew the radius of the Earth. Once again, you know the radius of the Earth, you know the masses, or you know your mass, you know your weight, which is the force of attraction between you and the Earth, you know big G. So then you can calculate the mass of the Earth. Okay. All right, now real quick, let's talk about, because a lot of these numbers are going to be really small or really big. So we're going to be using scientific notation. Now remember, on your calculator, however your calculator is set up, whichever model you have, I want you to use the EE key. That's the scientific notation key. So we have 6.67 times 10 to the negative 11th as our universal gravitation constant. Units would be newtons, meters squared over kilograms squared. In our calculator, we are going to enter that as 6.67. Then we'll hit that EE key. That'll give us a capital E. And then you'll type negative 11. So do not type 6.67. Hit the multiplication key, then 10, then to the negative 11th power key. Instead, it's 6.67 EE negative 11. And that just means move the decimal to the left 11 places. Okay, to sum up all of that, so we have our one equation for today, and that is that the gravitational force between any two objects is equal to big G, which is a gravitational constant, times the mass of the first object, so that could be this planet, times the mass of the second object, which could be this moon, divided by the square of the distance between the centers. It's always between the centers of the objects, which we're calling r squared. And once again, the reason that we're calling that r squared is because usually the moon is going to orbit that other planet. That was a really bad circle, but you get the point. So the distance between the centers ends up being the radius of the circle. Now, big G is 6.67 times 10 to the negative 11th. Units are newtons, meters squared, divided by kilograms squared. And then here's two constants that I want you to write down on your equation sheets. So the first one is that the radius of the Earth is equal to 6.38 times 10 to the 6th meters. So it's a little over 6 million meters. And then the mass of the Earth is 5.98 times 10 to the 24th kilograms. Now you can write on your equation sheet, you could write it as if you were punching in your calculator, or you could write it as times 10 to the negative 11th times 10 to the 6th times 10 to the 24th. From now on, and when we do our problems, I'm going to write it as 6.67 e negative 11. So that's how I'll write it on the board. Okay, So now let's do some problems. So let's go back to that question I asked you earlier. Why don't we feel the force of attraction between us and the person next to us? So I have two students who are 50 kilograms. And they're sitting 1 meter apart. I want to know what the gravitational force of attraction between them would be. So let's write down everything that we know here. We know the mass of the first object is 50 kilograms. And I know that the mass of the second object is 50 kilograms. So they're the same. I know that the distance between the two objects, you can write it as d if you want, or you could write it as r, is equal to 1 meter. And then there's one other thing I know. Anytime that we're calculating gravitational force, I always know the universal gravitation constant, big G. Big G is always going to be 6.67 times 10 to the negative 11th Newton meter squared divided by kilogram squared. I'm sorry I don't have my tablet on me, so that's as pretty as I can make it. Okay, so I have everything I know. Then let's write down what we're trying to figure out. We're trying to figure out the force. Okay. So as of right now, we have one equation, and that is the gravitational force between any two objects is equal to big G times the mass of the first object times the mass of the second object, all of that divided by the square of the distance between them. All right. And so big G is 6.67 times 10 to the negative 11th. I'm sorry, I'm going to drop my units. It's just too hard to write them so small. We'll multiply that by 50 kilograms. These I could probably write. The second mass is also 50 kilograms. And all of that will be divided by the square of 1 meter. Okay. So I need to pull out my calculator. 6.67, hit the EE key, negative 11, times that by 50, times that by 50 again. You could divide it by 1 squared, but you probably shouldn't, because that's just 1. And then the answer I got, my calculator put it in regular notation. I got to reconvert it. That's 1, 2, 3, 4, 5, 6, 7. It's 1.67 times 10 to the negative 7th newtons. Pretty sure I counted that right. Let me check. 1, 2, 3, 5, 6, 7. Yep, that's what I got. So 1.67 times 10 to the negative 7th newtons. And remember, if we wrote that out, like my calculator did for me, it would look like this. So that is an incredibly small number. Really, really small. And that's why you don't feel it. But that force isn't zero. And so if there was no friction, let's say on the ground, and I put you in the middle of, a football field area, but separated you from your friend by, let's say, 10 meters. So you couldn't touch them, you couldn't touch anything else. And I left you for a little while. If I left you for long enough and I came back, you would be closer together. At a certain point, you would actually be touching each other because that force would pull you together, even though it's not that strong. Well, in fact, it's incredibly not strong. Okay, so let's do a problem where forces are a little bigger. So I want to know, what is your force of gravitational attraction if you have a mass of 100 kilograms and you're on the surface of the Earth? So the force of attraction between you and the Earth, that's called your weight, right? So here the first mass is you, and you weigh 100 kilograms. I'm sorry, I said you weighed 100 kilograms. I meant your mass was 100 kilograms. We don't know what you weigh. That's what we're trying to figure out. The mass of the Earth is 5.98 times 10 to the 24th kilograms. So I'm writing it out just as your calculator would write it out. Now, it seems like we don't have enough information, but we actually do. Because the distance between you and the center of the Earth, that would be the radius of the Earth. You're really not big enough to make a difference. So here's the Earth, here's you. So really the distance between the center of the Earth and you, that's the radius. We'll get rid of my really cruddy drawing. So the radius of the Earth, the distance between you and the center, is 6.38 times 10 to the 6th meters. And then we always know big G. Big G is 6.67 times 10 to the negative 11th. And that is newtons meters squared over kilogram squared. Okay, so that's all we know. And then what we're trying to do is find the force. So as of right now, we have one equation to do this. And that is that the force between any two masses is equal to big G times M1 times M2 over the square of the distance between the centers. So the force is equal to big G, which is 6.67, E negative 11, and I'm really dropping my units because it's getting hard to write, times 100 kilograms times 5.98 is a 9 times 10 to the 24th kilograms. All of that divided by the square of the distance, which is the radius of the Earth in this case. 6.38, that is an 8, times 10 to the 6th meters, and that has to be squared. Alright, so before we even do this, my guess and check is going to be 980 newtons. Should be really close to that. And the reason I'm saying that is because remember your weight? We've been talking about this for a long time. Isn't your weight mass times the acceleration of gravity? If the acceleration of gravity is 9.8 and your mass is 100, then your weight should be 980 newtons. So this force should be 980. So let's try to confirm that on my calculator. I have 6.67 times 10 to the negative 11th times 100 times 5.98 times 10 to the 24th. And then all of that divided by 6.38 times 10 to the 6th squared. And sure enough, discounting rounding error, I get 980 newtons. So you can try that. You might get a slightly different number just because of the number of significant digits we use for the mass of the Earth and the radius of the Earth. But physics still works. All right, so that's all for now. Thanks, everyone, and I'll see you soon.